Right, so now I'm going to talk about A1 homotopy theory. And since I'm bad at type theory, mine is the traditional part. So yeah, I'll tell you what it is. The basic idea is to do homotopy theory like you do it classically with the unit interval for topological spaces, but instead use schemes and the affine line for the unit interval for parameterizing your homotopies between functions. And yeah, let me tell you about the standard classical basic setup. So you have smooth schemes over some base, and yeah, I really do the very classical thing. You look at simplicial pre-sheaves over these new schemes. You Zariski or Nisnevich sheafify those, or actually you do Nisnevich, but it's not so important, I think, for the things we see today. And you then make the affine line contractible in the following sense. So for every scheme X, we have this projection here from A1 down to. You invert all of these projections and formally add inverse to your candidate. And then this result is called motivic spaces. And that's where the whole thing happens.
Is there an op missing in the...
Yes, thank you.
And
Okay.
by the way, there's a series of talks by Peter available on YouTube from a couple years ago, where Peter was so kind to visit Verona and gave a course on motivic homotopy theory. So if you want to learn more details, go on YouTube.
Yeah, so in those talks I come up with a certain hexagon, but we don't go as far today. So why would you do such a thing? Why should you try and force some analogous thing to standard homotopy theory? Of course, because standard homotopy theory is great. Yeah?
What does the Nisnevich thing mean exactly?
You can, so the real
sheaves with the
thing that is, yeah, sheaves, you sheafify. You pass to sheaves.
So two localization, one sheaf and one.
Yes.
Mm-hmm.
Okay.
Okay.
That and that. And but I don't want to say what Nisnevich is. It's like Ital, but a bit coarser. But Zariski is fine for today. Yes.
Is smooth schemes over S maybe simplicial set enriched, or how do you get this Unida-like vertical map there?
Oh yeah, that's just you go here. That
Okay.
you can see this as discrete simplicial set.
Okay, fine.
Yeah, right. So this is a Unida menu. Okay, I mean this is the rough thing. Of course, you do it very traditionally with model categories, and this is a Bauswick localization. So what I would do. So okay, first, why do I want to do this? Because there's a bunch of invariants and functors that you traditionally study in algebraic geometry that go to something like sequences of abelian groups or so, cohomology theories, or for example, K theory of schemes that just are interesting and rich invariants, and they happen to satisfy, well, Zariski descent or the Zariski descent, and they happen to be A1 invariant in this sense here. We'll see an example. So for example, K theory for smooth schemes satisfies this thing that that this projection induces an isomorphism. Yeah, so it's just a place through which a bunch of interesting invariants does factor, and then you might as well try and study them here. And it turns out this is a very good place because you have homotopy theory available. Okay, so you can phrase this slightly bulky expression here in different ways. So one way to say this thing here is, okay, we have a topos here of sheaves. Well, passing from here to here, you could say it's a co-completion, homotopical co-completion. if I do just this Zariski thing here, then this is almost our standard model, right? It's okay, so there are a bunch of unrelated remarks. It's okay to actually take affine schemes here, and then we really have the standard model here. So why do I take smooth schemes to begin with? Well, because this A1 invariance only holds for smooth schemes. But still, I have all other schemes also here, because other schemes are co-limits of smooth schemes. Or anyway, I mean, not even because of that, because if I have any other scheme, I can just take the functor represented by that. It also lives in here, right? As a set-valued functor, which I then see as a discrete sufficient set. So all schemes are objects in here.
It's
Also
it's
non-smooth
for
ones?
the embedding there.
Yes, it's enough to test them on smooth schemes, I think. Is it?
I don't know. That was
Actually,
my question.
Yeah. I suppose yes. But I'm not sure.
I think
Anyway,
I think it's not
so this
important.
question becomes moot because we identify a bunch of things in the next step. So then it's a new question anyway, which schemes become equal and which not. We'll look into it. Okay, so this we could replace by just affine smooth schemes. That's okay because all the other smooth schemes also live in here. Then we just would set up the whole thing differently. And it would also be okay to take all affine schemes. It's just the case that, well, K-theory for non-smooth schemes, it wouldn't factor through this here, but instead we have something that's called A1 invariant K-theory. That's just the next approximation to usual K-theory that is A1 invariant. So
if S is a spectrum of a field, your scheme is say the thickened point, so you have the walking tangent vectors. So I mean, so a map from a smooth scheme into it should map just to the point.
right.
So we don't see the difference between the point and the thickened point.
That's maybe true, actually. Right, and it's actually true that this would happen anyway after localizing A1. So, yeah, but you're right.
Yeah.
So nothing is lost by actually only testing for smooth schemes because, yeah, reduction is invisible after. But okay. Yeah, let's look at the first easy thing that happens here. You can see here that different schemes may get identified here. So that's following. Let's glue together P1 from two copies of A1. Right, so they overlap in A1 without 0. And we twisted once for the one copy and we just included the other copy and then we get P1. Okay, so this is a push out, right? That's how we glue this thing. And you might as well do the following. You can just take this push out by 2 points, right? So A1 is contractible. This is the case X is a point here. And then we get the suspension of GM, or S1 smash GM. So S1, what is that? That's also living in here. It's a constant functor with value the substitutional set that represents S1. So, and we can point it and then smash it. GM, and you know.
Sorry, what
So-
is the smash product again?
Well, you have to choose a point in S1, so you can produce some concentrated set that represents S1, and yeah, point this one here at 1, let's say, and then smash product is really cross. So we can take products of functors, and we can take a wedge. We can take disjoint union, identify them at the base points, and then mod out that subspace.
So, like, We are modding out of functor in simple correctly.
Yeah.
Okay.
Take.
It's not point.
We identify
right?
so what is this? This again is it's a co-equalizer.
Ah, yeah, okay.
Well, of the inclusion of this here as a constant map and as the whole subspace.
Okay, thanks. This makes sense.
Okay, so maybe another one. So these here, since
Okay, just to understand it. So you take homotopy co-limits in the
I always
and then the proposition is that an ordinary co-limit is mapped to a homotopy co-limit.
That's right. That's what I achieved by Zariski sheetifying. So this means that usual co-limits here become homotopy co-limits there, like this one.
Yeah.
This is a new thing that didn't exist here. So this one is imported from somewhere else.
Yeah.
But now these
the
two
same,
things are the same because A1 is the same as a point, and I have two homotopy pushouts of two homotopy equivalent diagrams. So for example, that's a calculation here. So you can see that different things become identified. Okay, these are not two different schemes. Let's identify two different schemes. How about this diagram here? It's the same diagram as here, but I don't twist this time. I just take two copies of the affine line. What do I get? I get the affine line with a double point at 0. So that's also the same. It tells you that all kinds of things are not A1 invariant properties. For example, being separated, because this one is, this isn't, or being projective. Okay. So, you can actually do a lot, most of homotopy theory just in this way here, reasoning just with nice push-outs and infinity categorically. It's very comfortable. But the old way, of course, was to work with these model structures and do firing replacement and calculate a lot. And now what we can do in type theory in SAG is something intermediate here. We can work in this ambient topos here, and well, this localization, it's actually it's a Bausch localization, so it actually carves out a subcategory, a reflexive subcategory of this topos here. And it's actually localization with respect to a modality. So it's no longer a topos, it's a product preserving reflection functor, but not finite limit preserving. And so the idea is now to work with this modality. So what you would do to calculate this hybrid replacement in the model category is to produce some horrible explicit functors. And sometimes you're lucky and you don't have to replace your object, your scheme, for example, because it's already fibrant. So what does fibrant mean? It means, okay, it should be a sheaf, and it should be A1 rigid in the sense that, well, it has this lifting property. So if for any other test scheme, let's say U here, you find lifts up here. So there's no non-trivial maps from A1 to X. Let's do an example. So if X is a curve of G is bigger than 0, then it's A1 rigid. Why is that? Classically, I guess this is one of the things that will fail now, because, well, if X is, projective. If X is projective and I have a, let's just take U a point, I have a map from here, well, it will factor through some P1 here. But this would be a map from a genus 0 curve to a higher genus curve, which doesn't exist. So that's the intuitive reason why curves of genus bigger than 0 already are somehow what they are. They already are A1 rigid, and you don't have to replace them. But okay, that's a completion thing that we can't do in SAG.
Okay, what does A1 rigid mean? Sorry.
It means this here. For every such diagram there exists a
But not unique.
lift. No. Actually, would it be unique? Probably. I don't know. Oh, not necessarily, I guess. Hmm?
It will be later when we do it internally.
Yeah, I guess.
And where does this map now come from? Or what
This
do you
one here?
take for you?
Hmm?
What do you have to take for you?
Okay, I just gave the argument with a point here.
Yeah.
You a point, then this would be an instance of such a lifting diagram, and there it already fails for a curve of genus bigger than 0 because we don't have maps from lower genus to higher genus.
But,
I thought we want to show rigidity. I'm confused. What you? I thought we want-
Now we show that it's not vibrant in your model structure.
I think you want to show that the map from A1 to X is constant.
Right. That's what I wanted to show. Sorry. Yes. Of course. For a constant map we can do that, and that's the only map that exists in this. Yes. Okay. Right. And then of course we find this lift. Yeah. That's sorry.
okay.
I jumped a bit wildly here. Okay. What did I want to say? Actually, you can also shoo me away when I talk too much, because there's great stuff to say. Yeah, something similar works for abelian varieties, for example. You can't. They're already A1 rigid. So maybe here's another thing that connects to stuff we've seen. Another property that is not A1 invariant. So actually there's a counterpart to this, maybe I say that first. Let me, sorry I'm jumping, but GM is A1 rigid. It's also a good one to remark. Next to something Felix will say. Why is that? Well, it's enough to look at these things for affine schemes U, because we map out of these and everything else is a co-limit of affine. So, and let's look at such a diagram here, the multiplicative group scheme. Now this is a diagram of affine schemes, so it corresponds to maps. Let's just do this from here to, well, this is spec of some A, right? So this is AX. This is inclusion of A, and we want this to factorize. Okay, but these maps here, they pick out the units in A adjoint X, right? So this corresponds to a unit in A adjoint X, and this would correspond to a unit in A. So what we want is that all the units here are actually units in A. Well, now you see a point where smoothness comes in, because you know what's a non-smooth scheme? Like with such a thing here, this will have zero divisors. And with zero divisors, we can come up with units here which have higher degree, right? Putting nilpotent elements in front of the higher degree summons here. But if we don't have those, then actually the only units in the polynomial ring are those of the coefficients. So GM is A1 rigid, but only because we look at smooth schemes here. And so from there, let's not go into every detail here, but from there you also get that the Picard group is A1 rigid. Picard group, what is that? It's a functor, right, from schemes to groups. So it's something living in here as well, it's an object there. You can ask about A1 rigidity for anything that lives here, right? So again, it's true that for smooth schemes I have isomorphisms like this. How come? Well, this here is just a rough argument. So what do? I want to look at line bundles here over X. What are line bundles? Well, I could look at the category of trivial line bundles over X. What's that? Well, the automorphism of trivial line bundle is actually exactly GM. I make these two arrows for the category, but of course I only consider sheaves, or in this case stacks. If I stackify the category of trivial line bundles, I get all line bundles. So this is roughly that, but the GM is A1 rigid, and so the whole thing inherits the property, just as a rough sketch. It's not a proof, really. And so actually, from this you can get a little converse to what I wrote here. Just in parentheses. You can look at the pick 0, the n torsion. If you don't know what it is, then ignore this. Need brackets here. So this is something with the Jacobian variety thing. And for a curve, this is, I don't know, z mod something to 2 times the genus. So from this you get the genus is actually also an A1 invariant. And together with this rigidity, you get that actually these curves of genus bigger than 0, they also are not conflated in the passage from schemes to here. But okay, side remark.
I think I have a question about your examples upstairs. What if we go from GM to A1 and on the other hand from GM to star point? Because I can also do that, right? And if A1 becomes the point.
Yes, you want to go from GM to A1?
Mm-hmm.
Okay.
We go with a power twist, I don't care, because on the other hand I want to contract GM. From GM to point.
Okay.
So does the push-out exist in schemes?
Yeah, in schemes not, I guess, but in here it's co-complete.
Okay, so I cannot add this to the list of 3 diagrams up there.
Oh, here you mean?
The 2 diagrams there.
Well, something will happen like this, like happened here.
Okay.
It will be something mixed.
But I did not
I
find.
mentioned another.
Yeah, but I did not find.
So we'll form a cone somehow over this GM that identifies lots of stuff. No.
Okay, I thought for a moment that the push-out is the trivial scheme, and then I see that P1 becomes the trivial scheme, but this is not the case.
No, this is then not the case. P1 is.
Fine.
Okay, maybe the last thing, another example for the kind of computations you can do. And I mean, much of this here was pretty elementary, and maybe you get a sense that you can repeat these things. And actually, we'll see computations with Grassmannians and higher PNs. It's actually a important thing in A1 homotopy theory to compute the endomorphisms of Pn in this homotopy category. And okay, so taking homogeneous coordinates, you could represent these by, or could lift these to linear maps. And a funny thing happens here. So this has to do with, at least it maps to, and it's an isomorphism almost, to the Grothendieck-Witt group of the base scheme, whatever that is. It has to do with quadratic forms. It's an important invariant. But for example, here's a standard kind of computation that you can do that I'm sure goes through in type theory. You could look at this, the map from P1 to P1 given by this matrix, thinking of homogeneous coordinates. Since we are talking about homogeneous coordinates, it would be the same as a squared 1. I can just multiply everything with a constant here. Now this here is in SLK, let's say we have a field here, SLR, I don't know, let's say field. And here's a funny thing, so matrices in here, determinant 1, they can also be written as products of elementary matrices like this. This corresponds to doing some row operations. Okay, but such matrices, they are A1 homotopic, so maps given by such matrices are A1 homotopic to the identity map, because I can just morph this thing away. I stay in SLK. And so this means that, you know, multiplying such a thing by a square is actually the identity map in this homotopic category, which is sort of observation number one of a bunch of observations, which leads you to identifying this thing in quadratic form. So there's a bunch of somehow pretty concrete calculations coming from funny algebraic facts that just follow from this general setup here. Okay, why would you want to do this? Last corner here for me then. Well, there's really a lot of the landmark applications of this thing happen actually at later stages. So you can go to motivic spectra. You will see that K-theory can be represented here by a so-called motivic spectrum, and you can construct new cohomology theories and do stuff here. So here there's something like in topology. You have an infinite suspension spectrum functor, and you have an adjoint here. So you can sort of out of a spectrum get a sequence of spaces, and they represent the functors that you're interested in. And if you have representatives, you can calculate the endomorphisms, the operations of the cohomology theory, by looking at the representative spaces here. And that's actually something that's why this whole thing was invented, because this went into the blockade conjecture and with the operations of K-theory and of motivic cohomology. And well, that's one of the big successes that they computed the operations of K-theory. And you can actually do this at the level of spaces, and that's where we actually work, unless we want some ugly workarounds with spectra, but maybe we won't, I don't know. But so that's the thing that we could try to do, to take the spaces representing K-theory and try to compute the endomorphisms of those. There's also some nice direct applications about vector bundles here. They proved some pretty concrete things about vector bundles on schemes, like they proved that, I think it was really A2 minus finitely many points, only admits trivial vector bundles over a field. Stuff like this, very concrete stuff you can get out of computations in these A1 homotopy category. So I don't know those proofs. I really worked more in this area here, but I think there's stuff that can be done just in this setting. Okay, so.
Yeah, okay, I guess I make some space. Start. Yeah, it's a bit hard to decide because, I mean, this one can go. Yeah, maybe I'll start here.
Technical question, is the recording still running?
Yeah.
Awesome.
You're very quiet.
Yeah, good. So I'll start somewhere around here, this place, and define the localization at A1 as a modality. So definition, let shape A1 or alternatively just shape for now, be the nullification at A1. You might wonder about this. Here we take more maps which we invert, but this happens automatically since modalities preserve products. So yeah, so this part is slightly simpler. And just to remind you of one way of viewing this is that it means when a type is modal, or a type is modal if and only if any map from A1 to it is constant, which you can express as this map being an equivalence. So this means X is shape model. And yeah, so the point is always modal. That's something we get for any modality. And here the next best example, which is already very interesting, is that types with decidable equality are modal. So maybe let's start with this. So proposition, if X has decidable equality, then, which includes in particular all propositions, which are always good to think of, equality, then X is already shape A1 model. And so for the proof, we kind of use this intuition. We take some map from A1 and try to see that it's constant, which we also have seen starting here. So let's just give it a name. And we have a point in X, so we can rewrite it as, which is now in particular for types with decidable equality, we can rewrite X as one point, which we kind of think of as gamma of 0, let's say. Could also take gamma of 1, of course. And we can then rewrite as the coproduct of this point and all other points. So all x in x, which are different from this one thing. So. Okay, so we have a map to this type, but from this type we can map to bool, or the 2-point type. And we learned by mapping this part to one element here and this part to the other, of course. There are different maps that wouldn't have. And we have learned in Matthias' talk that maps like this are constant. So, constant. Yeah. This is constant. So, we're done. And yeah, and this involved some calculation which used the axioms. So at least SQC and that are as local. Okay, and one interesting algebraic example is corollary. separated étale schemes are shape model because they are known to have decidable equality.
Unramified would be enough.
Unramified, yeah, that's better. Should fix this in the notes. Yeah, thanks. Yeah. Okay.
How do we know that we don't get to divide out too much? So,
Yeah, I mean,
at the
at
beginning,
this
so we
point,
start with smooth schemes. So now we have lots of more types, and well, could be that even for smooth schemes we identify now too much. Maybe we can take a detour via some non-smooth thing.
yeah, I mean, that could happen, and I guess the only way to know it doesn't happen is to show off enough types that they are modal for the modality.
Yeah.
Or to show that in the classical case, all these maps also for non-smooth schemes are involved. Regarding the smooth one.
Sorry? What?
Yeah.
But we also have types that are not. So
Yeah.
For any X that is in this category. I think that's just true.
True.
What was the agreement?
What we have some kind of fiber-wise equivalent pre-sheaf category.
Yeah.
And then. Oh, no. For the representatives, we have this equivalence.
So I cannot just denote anything as a co-limit of representative.
Yes, right.
That's enough.
That's
So when you wrote x times a1 to x,
Yes.
translation is this, you meant x is a smooth scheme? Or
I meant that, but
Yes.
it's just not because of set theoretic stuff for both localization, a
Okay.
set of morphisms, but then the consequence is that for any other object in this category, the same chain projection also becomes equivalent. And that means we don't invert too much.
Yeah. Okay.
Okay, good. Then I don't worry too much. And yeah, so I mean, something that is different, which was already explained somewhere, I think, or mentioned, is that A times is not rigid, or GM if you want, but it's almost. So we have only to slightly correct by taking the formally étale replacement, which looks almost the same. So this happens to be A1 viewed as a ring and units in that. So, I mean, we didn't talk about this too much, I think, but the nil radical in A1 is exactly the formal disk. So all elements which are not zero, and these are kind of the ones infinitesimally close. And when you mod out the nil radical as a ring, you can imagine you mod out at every point infinitesimal neighborhood disk. And it gets a bit smaller. Yeah.
And then exactly we don't have any of these polynomials with higher degrees.
Yeah, exactly. So it's to make this go away, but the proof is a bit ugly. But
Sorry, AX, or the unit in A1 or?
yeah.
GM.
Yeah. Okay. So, I mean, usually the argument you would use is what Peter showed us, that you, I mean, in our case, you can just see maps like this, which we should prove to be constant, are the same as algebra maps in the other direction. So it's something like this. And then you know it's given by a unit in here. But yeah, as we noted, there could be nilpotent stuff going on, so it's not just a unit in the base ring. Yeah, and what we do instead is we look at, so step one is we prove that this thing is modal for our modality, and let's not worry about step two, but yeah, so let's see its model. So we have the, let's give it a different name also. We have the model replacement.
Okay, but step 2 is something like one modality is finer than the other. Or not?
No, step two, I would use a lemma about modalities, which says if the fibers are modally connected of some map into a model type, then it's already a model replacement. Okay, so we have a surjection like this, and now we can just, so the goal is to end up with a map here, see that it is a unit plus some nilpotent stuff, and then use that we identify nilpotent stuff here to see that this map was actually constant. And we can use that to get a map upwards, or at least some approximation to it. We can use the risky local choice. So the point here is use the risky choice on this type. So we have for all x in A1, which we can use choice of, exists a pre-image of the image of gamma here. So a y in A times, such that gamma of x equals the modal replacement of y. Maybe let's call it this one pi of y. And then I get a cover of this one and lifts on each part of the cover. So I have some SIs here, some DFI. So I get sections SI, and what I know is they agree not on intersections, because after mapping down again, they are not equal, because I define not equal things in here, such that not SI equals SJ. And now I can prove it, I can use it to prove some double negation. Use to prove for some x in A1, gamma x is some fixed value. And yeah, I mean, you prove it not, and how can you do it? If you have a not, you can glue your sections and then use this representation. Then you can use algebra, and then you have a constant value. Okay,
So
I
what-
think I know now why you said you don't understand this proof. I'm a bit doubtful.
And what's the universal quantifier? No, so for all, so there is an A0 such that for all x in A1,
Yeah,
not
that's a problem. I just noticed by writing it down, the quantifier is in the wrong position. Like if I have my pi here, so I get an A naught under the not because I use this one inside the not and then produce this value. Okay. Yeah.
No, I don't understand this.
Okay. Yeah. Sorry, it made sense around 1 a.m. I guess. I don't know.
Can't we, I mean, what about showing like gamma x is gamma y? So for, I mean, you start with for every x
okay.
and y in A1, you try to show that not gamma x is gamma y.
Yeah, maybe I just quantify wrong. Yeah. That's something I can do. Yeah. Was it enough?
Do you mean SI of y? Or do I understand? It's not the same one as before.
Yeah, I mean, maybe I should say more. If I want to not get something, I can assume those are equal, glue them to some section. So not, I have a section here. Then I can use this algebraic lemma that I have some polynomial, which is a unit that describes this function. And then I know all images of this map are equal up to some nilpotent difference. And I know they are equal here. So I definitely get this one. So okay, so there's some open question if this is enough, because it's only some weak constancy, I guess you get. But yeah, so I think maybe we shouldn't spend time on it now, but move on to the Grossmanians, because that's something we definitely should look at. And this is an exercise for later. If it's not.
So actually I have 5 minutes left in principle.
In principle.
In principle, not in reality.
We learned about blow-ups this morning.
So the lecture can go up.
Yeah.
Okay.
Yeah, no.
Okay, that's
What about
the answer.
But I mean, blow-ups, but the exception device is still compact, so.
So I should, yeah, okay. I will
Well, on
use
the
a
other hand, it has
compact
no
amount of
boundary,
time.
so yeah.
Okay, so we already presented one result, which was that, so okay, let me write it this way. P1 is A1 equivalent to the suspension of A times. So Peter presented this, and I mean the proof works exactly the same synthetically. Okay. So now I will present an extension to higher projective space around similar ideas. Yes.
When you say A1 equivalent, you mean after
So I mean there is a map
A1 equivalent.
that is after A1 localization
Yeah.
an equivalence. So it means if we try to see them as motivic homotopy type, assuming A1 localization works for this, then it means they represent the same type. And so, okay, and so now I will give a short explanation. So,
In suspension, we can always think of the unpointed one, like join was S0.
yes, yes. So I mean, me by suspension in this context, I mean the homotopy push out of this.
Yeah, which is, yeah.
So, yeah.
And Peter called it the smash with A1. With
Yeah,
S.
but I like this better because you had to choose base points and they came out of nothing. I mean,
Yeah.
yeah.
They both are equivalent. Yeah. So okay, so remark which is well known is that the projective space is actually okay. Let me use A here. It's actually an plus 1 minus 0 quotiented by A times. And so there was one question: how can we represent this in homotopy type theory? And so here there is a trick, let's say. So if you have a zero group, for example, A times, you can define the delooping of A times. So, for example, you can define it as the type of R module such that V is merely equal to R as R module. And so here you have a type that is clearly connected. So it has a point which is simply the R module R. And if you try to look at what the path space of this looks like, well, you see it will be the type R is equal to R as an R module. And this is actually A times. And so I will omit, so you can check that the concatenation of paths really correspond to the multiplication in A times and that this correspondence kind of works. And so now you have a type with a point and a group of loop, which is A time. And so then you might ask, but what is the action of A times on some type? What does it correspond to? And so here I will give a definition. So an action of A times on X, the type, is, and so it will be a map, say 5, from B A times to type, such that phi of the base point of B A times, which I will call star, is equal to X. And so why does this work? So you have a map from B A times to type. And so by the universal property of BI times, which I did not explain properly, but you can see that this corresponds to giving an image of the base point, so the type here, and map from A times to the identity type to X equals X in type. But X equals X in type is the type of equivalence by univalence. And so this corresponds indeed to an action. And so one thing which is nice is that here we can use any type X. We don't have to deal with any coherence or anything. And so now let me go to quotient. One more definition. Let say phi be A times to say type be an action. On X, then we define the homotopy quotient of X by the action. So I will just write it this way where the action is implied. And this you can just define as the sigma type over any V in BA times of phi of V. And so here, what does this correspond to taking the quotient? Well, you see using the base point of BA times that for anything in phi of the base point that is in X, you will have a point. But then you also had for any path in BA times some path linking this point. And this actually gives you the quotient. And so now we want to present the projective space using a presentation like this. So let's say it's the remark. You have that Pn is actually equal to the sigma type over V in BA times of V to the power of n plus 1 minus 0. And so here V is in BA times, meaning that it is an R module which is actually equal to R. And this definition work as we make the R module vary here, we are actually mimicking the A times action, on Rn. And so now we want to try to understand what this looks like up to A1 homotopy. So we can try to understand this piece a bit better. So say lemma for n Vn minus 0 is A1 equivalent, and so here so I will use V times and I iterate the join n times. So the join construction, I forgot to define this. So the join of A and B is defined by, so we take A times B, we take the two projection, and then we take a homotopy per shot of this. So it means we have a copy of A in the join, a copy of B, and for any 2 points, one in A, one in B, we had a path between them. And so you can iterate this joint product, and that's what I use here. And so, okay, let's prove this. So I will not be very precise in order to go fast, but the idea is simply here you take something like this. Here you send it to V times Vn minus 0. Am I getting confused? No, no, no. Here time Vn. And here it's just Vn plus 1 minus 0. So I have a pressure like this. Yes. And so now let's A1 localize.
I had a question about what you just raised in the definition of the nerve. Do you need to truncate the equality of R modules?
Yes.
Because I mean, by univalence, an R module can only be equal to R in one way, right? Like if
No.
Otherwise it would be isomorphic to R, right?
If you multiply by an invertible, you go from R to R, you have the linear map sending a point in R to the invertible times the point, and
Maybe you meant
this is an equality.
maybe you meant by univalence there is only one R module equipped with an equality to R. Is that what you meant, Max?
no, but that's true. Yeah.
The singleton is contractible, but that's why we don't write the singleton, but
If I-
truncate the equality type.
Yeah, that's true. Okay. Yeah. Take it back. Sorry.
Okay.
Yeah.
Okay, so now what happens if we apply the A1 shape everywhere? Well, this Vn here will be sent to 0. This V as well. And so let's say up to A1 equivalence. This diagram. The diagram is just V times n minus 0. Here I go to Vn minus 0. Here I go to V times. And so here I get the A1 replacement of, yeah, okay, but let me not write it this way. So here I use induction on the number n. I know that this is actually equivalent, A1 equivalent to V join n times. And so here I get the join V times n time. And so what that means is that up to A1 equivalence, I have that this is indeed n plus 1 iterated join here. And so, okay, and so now we, so from this, we get that Pn is A1 equivalent to the sum on V in Bi times of V joined n times, n plus 1 times, sorry. So, okay, which is it's a formula, and it gets particularly nice when we do this for p infinity. Because then, so p infinity is the colimit on n, a natural number of Pn. So you have an increasing map, but actually you can swap the sequential colimit with the sigma types. So you get that this is a sigma over v in Ba times of the colimit over n. Of this thing, so up to A1 homotopy. And actually this colimit is contractible. So if we look at the map, the various map I used, we see that this colimit is actually, you start from, sorry, it's V times here. Otherwise, it will be contractible. And so you start from V times, then you included in a join of two copies. So you include it simply by using the inclusion on the left. And then you include this similarly by using the inclusion on the left, and so on. And so actually, since V times has a point corresponding to the 1, and it merely has a point corresponding to 1 in A times, we know that each of these maps are constant. So because we include V times as a copy, we know that every point of this copy is joined to the unique point on the other side. And so all the maps are constant, and so from this we get that this colimit here is actually contractible. So it's actually exactly the same idea behind the proof that the infinite dimensional sphere is contractible. And so yeah, so from this you get.
Yeah, I mean you construct something like EGM.
Yeah, exactly. Yeah. And so, yes, so it's an example of a little computation which works synthetically without any trouble. One thing which I think is a bit interesting is that actually if we think about what we used about A times, we used relatively little. And so, for example, if we were to start with Z over 2Z as a group rather than A times, we could carry out a similar construction and would end up with something that could be interpreted as saying that the real projective plane at infinity is equivalent to B to Z over 2Z. So here the analogy between Z over 2Z and the real line is that the invertible in the real line are homotopy equivalent to Z over 2Z. And so I think I will stop here. There is a similar computation for the Grassmannian. I can just give you the result. So if you define so this is the k-dimensional subspace of Rn by definition, and then you can define gr infinity of k as the colimit of those, and you get, using similar ideas, that it is well, b of g and k. So when k is equal to 1, we find back the result as mentioned about projective space. Thank you.
that's a thing that you use for computing endomorphisms of either the vector bundle functors or the K-theory functors. Of course, can use the BGL-Ks to represent K-theory later on with BGL, coding of those again. And then on the left hand, if you take endomorphisms of those, on the left hand side you take the Grassmannians, which are a colimit, which you pull out of the Hom. Then you have actual small cellular schemes, which are very computable on K-theory, and then you get the endomorphisms of K-theory.
Okay. So I mean here the synthetic results are really very in a very early stage. And I mean one problem which I thought about a bit and I had no success is how to have the Nitsievich topology synthetically. So presumably it corresponds to a modality which is somewhere in between Zariski and et al. But I don't even have a strong candidate on how to define it or anything. If someone has an idea.
So, I mean, in topology, I mean, these spaces are classified spaces for vector line bundles.
Yes.
So, what do they tell us here? So, I mean, we don't know whether all bundles on AN are trivial, but we can force them to be trivial in some sense by inverting A1. So maybe we make the theory a bit more accessible, and we should better redefine what a bundle is, namely. And so the question is now, so what do maps into P infinity and maps into PA times parameterize? I mean, after inverting A1, they become the same. And this would maybe it's then a good notion of line bundles.
Yes.
So,
Sorry, what was the reason that we should redefine bundle?
now, classically, I use P infinity or PGM as a classifying space for line bundles. So we can try to do the same here. Just take a look at maps into these spaces.
Yeah.
But these are only equivalent. I mean, when we mod out A1, which means that our line bundles, I mean, they should not see multiplying on A1. So somehow we force line bundles on AN being trivial.
Yeah.
And the difference should be detected on one of these two sides. So, so my question is, can we write down more explicitly on one in very simple terms what are maps into P infinity and what are maps into P?
So the right hand
GM.
side is, I think, easy for me because so the type BA type, so BGM is equivalent to the type of, I think as you wrote before, of R modules that are merely equal to just R1. And this I would call the type of lines, and the line bundle is I would define as the type of maps to the type of lines.
Yes, yeah.
So the right hand side is
that's exactly kind of answer I
the
wanted to get, yes.
elementary definition of line bundles.
Line bundle, yes.
Yeah.
And now
But
the
the left hand side.
And what about X arrow P infinity? And here I don't know how to compute this.
yeah, but that should be something like when we force line bundles on AN being trivial. No.
I mean, but still,
We can use Zariski local choice in order to obtain a bound on the number n, right?
I don't know, but sorry, a map into P infinity cannot be the same as a line bundle up to isomorphism, right? So what is exactly the classical statement? Because there are different points in P infinity, so that from the point to P infinity, for example.
You mod out homotopy.
Yeah, the classical statement is for smooth schemes, the A1 homotopy classes of such maps correspond to line bundle.
A1 homotopy classes of such maps. And what is an A1 homotopy class?
Well, it's something in that category after inverting the
So the Hom set in the
Yeah, we are in this category, so this is Yeah, I think we can get a bound.
So how do you want to get a bound?
But I misspoke earlier. I said by there is local choice, but instead by boundedness. By the boundedness
No.
result.
So how do you get a bound? How do you get a natural number for every point or something?
Well, I have a map. No, okay. There is local choice and boundedness. We need both.
Okay.
Because I mean,
That's
get
useful.
a point in P infinity is represented by a natural number
Oh,
and an element.
You start with a map from x to p infinity.
Yeah.
Sorry.
Yeah.
Okay.
Yeah, okay.
Yeah.
So we have maps into Pn.
So you want a finite presented scheme in the category sense?
X should be a scheme
And then it has to
in
factor
the
for
sense
one
of
of the
SAG, so finitely presented. Yeah.
I think he meant compact category.
Yeah.
I don't like the word for there.
But I don't think
Right. I mean, if we have a map to Pn,
Yeah.
so the map to Pn is the same as the rank 1 quotient of the trivial bundle over X, and the trivial bundle has rank n.
Yeah, the question is
And now we can stabilize.
The question is whether we actually have a scheme morphism that represents our A1 homotopy class. So we have to ask whether P infinity is actually A1 rigid.
So let me try to summarize this. So if X is a scheme, we know that any map from X to P infinity factor through Pn for some n. So nearly. And so from here, do we know what maps into Pn classify synthetically?
Into
Pn, I think this is,
Yeah.
this is you just quotient of bundles.
A line bundle.
Okay.
The line bundle realized as a quotient of the trivial line bundle. Because over Pn we have this we have the rank n plus 1 bundle, and O1 is a quotient. And then we just put back the quotient to X, and this is what classified.
Okay.
And the stabilization, so when you go from n to n plus 1, it's just adding a trivial bundle, a trivial line onto your, just quotient it out.
Mm-hmm.
So this is how you get to P infinity.
Okay.
Yeah.
So from what Hugo already proved, okay, I think I just don't understand anymore what we're trying to prove, because this already tells us that A1 homotopy classes of maps to P infinity and to P8 times are the same.
Yes.
We have actual maps now, actual scheme maps.
Yeah.
And so we have a map from P infinity to P A star, I think. Not just in the A1 category, but literally. Because these maps to P infinity give us line bundles, and those correspond to something to a map to P A star, so we can just post-compose.
Yeah, I can turn any point.
And now the question is whether every line bundle comes from one of those PMs.
Okay.
every from the old line bundles.
Yeah. So an actual line bundle on a scheme, does it come from a map to P infinity? Is that what we're trying?
That's a question.
That's
what I just asked.
I understand that this is a question, yes. So in other words,
For example,
every
if
line
X is a point, you get a line, you get a point in Pn, you want to find an A1 homotopy to some chosen point in Pn, presumably?
This sounds like a different question. So are you asking that in which sense two maps to P infinity are the same when line bundles are the same? Is that what you're asking?
Can you repeat it?
Maybe you should repeat what you said. I think I didn't understand. So you talked about 2 points in.
So I mean, so So I mean, if I understand correctly, what we want is that two maps from X to P infinity representing the same bundle have an A1 homotopy between them.
So that's injectivity of some map, right? And I think what Peter before us was something like surjectivity of perhaps the same map.
So, but aren't there schemes without any maps to PN, without any ample family of line bundles? And they still have a tangent. No, wait, no, that's.
Can we write down the map you are talking about? This, what are you talking about?
Yeah, I think I can write down that. But will be not satisfactory. So are we fine with the statement that a line bundle on a scheme X is simply a map from X to this type here? Okay. Then I want to turn a map from X to P infinity into a map from X to here, so to a line bundle. But for this, I just have to find a map from here to there. And I can write down this map. How do we go from here to there? Well, I take a point here. By definition, it's a point in some Pn. And
this map is just O1.
Yeah, okay, I can call it O1, yeah. Does that help you?
Make it more precise.
Yes. So there's a canonical line bundle on every Pn, and it's always called O1, and it looks like this. It takes a point in Pn and says, oh wait, what is Pn again? Pn is the set of all lines through the origin in A to the n plus 1. So a point in Pn is a line in A n plus 1. I take that line.
No, the dual.
So, the dual, if I want O1, yes, okay. I don't know
Okay,
why.
so you are O minus 1, I'm sorry.
O minus 1, yeah, good. So the tautological line bundle is, tautological, okay, I have real problems writing it, but if you want to write in homogeneous coordinates, I think I can write this is sent to this vector, right? So this is a subset of R to the n plus 1, but it is also an R module. And this R module happens to be a line in the sense that, yes, merely it is equal to just R1.
Okay, is it well defined if you pass from n to n plus 1?
It is.
Yeah.
When we pass from n to n plus 1, I mean...
Then we get an additional...
This will be defined, right? Then I get an additional 1 here, right?
0.
Zero?
You extend that 0.
Oh,
because
yes.
because
Get
there's
additional
already
0.
1 invertible, so you can just add 0.
So we get certain lines in R to the n plus 2,
Yeah.
but indeed from a line in R to the n plus 1, I get one R to the n plus 2. I mean, there's an embedding, and that's what happens, right?
Yeah, so the embedding is also by embedding zeros.
Yeah.
Right?
Yeah.
The same is true here for the Grassmannian. When you have k-dimensional subspace of Rn, I mean, you have to map it somehow to a k-dimensional subspace of Rn plus 1 to get the inclusions between the Grassmannians.
Yeah.
And so you have to say how to, and you just extend by 0.
But once you have this map, presumably you would want that if 2 points are sent to the same element here, then you have an A1 path here. I mean, that's what I understood. And this would mean that for any 2 points in P infinity, you should merely find a line joining them, and that doesn't sound doable.
Actually, that's formalized.
Oh, really?
So now let me be more
So ACTA
precise.
is inconsistent, or?
Okay, yeah, then ACTA is inconsistent. You asked that for any 2 points in P infinity, but instead I can say any 2 points in Pn, right?
Yeah.
I find an A1 line through them.
Different points.
As you said now, it's not true, but I think it's true if I have 2 different points in Pn, then I can merely find a line through them.
Yeah.
And then if I have two arbitrary points, I can find a line through them or two lines through the third one.
You can
And that is
play
enough, I
like
guess, right?
zigzag.
For I want homotopy. I mean, I can chain homotopies.
Yes, chaining them, yes. Chaining them in rows. Yeah, good.
Maybe these things would be simpler to argue about if we know what we can do with R infinity.
What do you want to do with it?
Yeah, where we have to check with which construction this co-limit all commutes. So that we can just, I mean, because all arguments we just had were something like, okay, we would like to say something about P infinity, but well, it happens already on Pn, and then we have to glue again. And
But I mean,
maybe it would be nicer to just say, well, where we have lines in R infinity. So this is P infinity. I know we have, but I'm not sure whether this is true naively.
is P infinity the set of all lines in R to the infinity?
This is probably wrong.
Yes.
In this naive sense.
Really?
So this,
Yeah, it's a co-limit, so they all live in some finite stage.
Yeah, but what do we mean by R to the infinity?
Yeah, you
We
can
need to
build it
take
as a
the-
co-limit.
Yeah, but then you can still find a crazy line that uses all constraints.
Yeah.
What?
yeah.
What do we mean by? But we mean line through the origin, right? So every line is represented by a vector.
But then you take.
But if by R infinity
Okay,
I
yes.
mean the
I see.
countable
Yeah, maybe that's
sum of R's, then every vector,
Yeah.
so every element of that has only finitely many non-zero entries, right?
Okay. I was
So if
okay.
that is what we mean by R infinity, then
Yeah.
I think it works. I think that is P infinity.
And then you argue again somehow by boundedness, because when we look at families of lines, that we can still only produce finitely many non-zero coordinates in R to infinity.
So if the family is indexed by some scheme, you mean?
Yes. Yeah, but it could be indexed by something. I mean, it could even be indexed by R infinity.
Okay.
So.
How do you get this? Just a second.
And what was the advantage of this one?
Well, we can write down this O minus 1 without any more arguments.
Right, okay.
Oh, okay.
For example,
Yeah.
and we can also,
Yes.
and the idea is also that we know what a map to.
The only thing I have to change is write infinity here, right?
And infinitely many zeros after the end.
Yeah. If you think that's necessary.
Okay. So it's also true that in BA stars, so the A stars in Abelian group, so BA stars is in a Abelian group. I'm not sure how, but if this works in out.
It is an Abelian group again, you say?
Yeah, I mean, in homotopy theory it is.
I mean, here
I mean,
it's
it's
it's not a set.
But the higher things don't exist, or what's the status here?
I mean, we can say a higher group is something which is a loop space.
Okay.
And yeah, what happens
That's
in the case.
okay.
But don't we
So-
also have the multiplication immediately available? So given two lines, we can form that tensor product?
Yeah. Yeah. So classically it's true that on the left hand side this corresponds to the single embedding.
Wow.
But it's also something one can check.
Some infinitary separate embedding, yeah?
Well, any 2 points come from finite stages and then they go to
Ah,
n plus n plus 1 or something.
okay, I see.
Do you think it will be a good homomorphism with those two group structures?
Where but in P infinity
Infinity maybe is not.
we don't have negatives, do we? We don't have inverses. Or do we? So how does liquid embeddings work?
Yeah, what's the inverse? That's point.
Shouldn't it be the dual because it works with line models?
Yeah, but how do you find the dual? So I mean, P infinity is the co-limit of all these Pn's, but you said that I have one in Pn and one in Pm. And then I add them, then I get something in P, something higher, right?
Yeah.
So to get, but the neutral element will live in P0. Right? So
Yeah. So P0 is also embedded to P something higher. So it's not
right,
excluded that you land there after adding something.
right, okay, I see. And what? But is it clear what you mean by dual? I mean, what is the dual of the point in Pn?
Okay, it's not clear. At least not to me.
Yeah, no.
But there's a map you can check. So the one multiplication is respected by the of -1. Right?
That's interesting.
Okay.
And we have this problem of Felix at the end with not.
But it just works.
Yeah, I mean you can just we just choose for y one of the points.
Yeah.
And then you have your base element, right?
Yeah, it's weakly constant, but I failed to realize that this is enough because we have a point in A1.
Yes, and then yeah.
Yeah.
Okay.
Thanks again to the three speakers.